Hi everyone, my name is Vincent, and I'm a research advocate at Rasa. It's my job to make sure that our community of developers understand the algorithms that we design, as well as to explain themes in NLP in general, such that people are well equipped to understand how digital assistants work. And today I want to talk about transformers. They are a relatively recent addition to neural network architectures, and what I would like to do is explain how they work, and also why. The main idea is to leave you with a lot of intuition, and I figured that before diving into slides and theory, what I'll do first is show you a demo of a digital assistant that's running on my computer. So let's check that out. Okay, so I have a Visual Studio Code instance open, and I'm going to draw with this pen, which is why I won't always be looking at the webcam, because I've got a second display below here. But for all intents and purposes, what we have here is a Rasa project. And what I'm just going to show you is one configuration file and what it's supposed to do, because this stories.md file, by and large, if you're a little bit unfamiliar with Rasa, this is how we define a flow of a conversation. And in particular, what I want this digital assistant to do is relatively simple. I want it to do counting. So let's say on the left-hand side, I've got my user. And on the right-hand side over here, I've got my trusty digital assistant. And these two are going to have a conversation. And the main thing that this digital assistant needs to do is when the user says, hey, could you start counting? Then from 10, the assistant will start a countdown. And after every count, the user must affirm that indeed we can keep counting. So every time the user says OK, assistant says a number, it gives control back to the user. That's what the happy path is. But what the user can do is the user can perform an interrupt. For example, the user could say, hey, are you a bot? And it's important to get that question right. We don't want our digital assistants to pretend to be human. So in this case, the digital assistant needs to stop counting and needs to immediately confirm that, yes, I'm a digital assistant. And immediately after that, I would not want my digital assistant to give control back to the user. Instead, what I would want it to do is perform one more count and then give control back to the user. And what's interesting about this situation is that it's not necessarily a one-to-one mapping between the intent of the user and what the assistant is supposed to immediately do. It needs to keep track of the history and of everything that happened in the conversation so far in order to be able to recover here and count the next number accurately. And that's what you see represented in the stories.md file over here. We have intents from a user that get mapped to an action, which for all intents and purposes, it's like a one-hot encoded action. So it's not like it's generating text. It actually has to predict the action correctly. And the user can confirm a few times. But for example, here we have a bot challenge. And, then we need the assistant to utter, yes, I'm indeed digital. I'm not an actual human. And then it needs to start counting again. And only after that are we going to give control back. So what I've done is I have pre-trained this assistant, and I'm just going to go and talk to it. So we'll just make this a little bit bigger. There's a little bit of text here, but we'll just say hello. It says hey back. I'll just tell it to start counting now. It says okay, ETA 10. I'll say okay. I'll say okay. I'll ask, are you a bot? And in this case, it's doing one thing correctly. It's saying that it's a bot, not a human, but it's not counting again. So it's missing a step. And if I were to say OK here again, it says end of countdown. And if I start counting again, it starts at 10. So it's not doing the right thing here. It's messing up is what's happening. And the reason why it's messing up has to do with this one number in this configuration file. It's this one. It's the maximum history that this TED policy is able to use. And this TED policy is a policy mechanism that uses a transformer. So what I would like to do now is explain how this transformer policy works, and then why this history number needs to be big. So this is an opportunity for me to dive into the theory, and at the end of the talk, we'll come back to this digital assistant, and we'll fix it. We'll make it such that it is able to handle this use case. So let's go to the slides, and let's talk about the theory here. Okay, so given the example that we just saw, let's talk about digital assistants in general. So let's now consider a different conversation, one that happens between an assistant that is able to order a pizza for you. You can say hello, and again, we can say hi back. You can tell the assistant you'd like to order a pizza. The assistant asks what kind. And again, here also, we can have a frequently asked question or some form of chit-chat happen that we would really like to be able to pick up appropriately. And then immediately after, still be able over here to pick up the conversation where we left it. So I would argue here that it's not so much an edge case that we have conversations that need to be picked up later. It's a general thing. And if we think about the algorithms that you might need for this, I mean, let's just look at everything that's happening in this conversation. We have intents, which are like what the user just said is something that we'd like to detect. So the intent of the message, we have an algorithm for that. We also have an algorithm for entities. And you can imagine that that's pretty much a one-to-one mapping. We get one sentence in, and then we have some features that have to come out of it. But the actions that are taken, that's substantially different. The thing with actions is that it doesn't just depend on this intent or the entity that's in the current utterance. It actually depends on how the entire conversation has been going. There's a time aspect to it. We have to look back. And the trick would be not to just look back one time step, but possibly many time steps. And we would like to have an algorithm that is able to handle, this time aspect of the dialogue, as well as able to get these intents and these entities as inputs as well. So considering the fact that we have something that's happening over time here, it might be interesting to get an analogy going with what people do in time series typically. Because when you have a time series, what you can do is, over time you have a signal and that's a little bit noisy. So what you could do is you can apply maybe some sort of a filter where you're taking a weighted average over points that happen over time. And the current GIF demonstrates this, how you can reweigh. But I can also draw the summary line that we make as part of this GIF. So it depends on how you want to do your reweighing. There's hyperparameters for that. But you can imagine that the thick red line, the one that's on top here, you could argue that perhaps that's a more contextualized time series than the raw data that we start out with. It is more smooth, and depending on what we're interested in predicting, that smooth line is going to be more useful than maybe these noisy data points that we have over here. But it would be nice if we're able to repeat this, not necessarily for a time series task, but for a natural language task where we have a sequence of conversation happening. So let's pinpoint how this works, and then we'll see if we can do something similar for text. So as far as xi is concerned, there will be the data point that is over here, this one. But as far as this one single data point is concerned, in this time series task, it needs to pay attention to its neighbors. And it needs to pay more attention to its closer neighbors than to its neighbors that are further away. For a time series task, that makes a lot of sense to shift your attention in that fashion. And then, once you know where the attention has to go for that one data point, well, then you can apply a weighted average. And that's what this red line is over here. So we go from this original point over here to a more contextualized point that's smoothed out. And that's what this operation does. It's adding a little bit more context for the task that we have at hand. But how do we go about that with text? So for text, recently, we have these word vectors at our disposal. So we can represent words that are in a sentence numerically. So what you can do is you can say, well, I've got these tokens, and for every token that I have in a sentence, I have this vector. And this is an array of numbers, and I have that for every single token. But typically word embeddings, they are static. So that means that the word embedding for bank is the same in both of these sentences. Although I hope that you would agree that the meaning of the word bank of the river and the meaning of money on the bank depends on the context of the sentence that it lives in. So if we are going to do some sort of smoothing and contextualizing, it will be nice to do that, but we're going to need to have something other than distance, so to say, to get there. And that's because proximity in a sentence doesn't necessarily imply a high correlation or a high relevance. In this particular case, I hope you would agree that to get more context to this token for bank over here, we have to look at what river means, and to get more of an idea what bank means over here, we'd have to look more at money. So we cannot use distance as a reweighing mechanism. We have to do something else. So let us observe one thing now, though. Because if we cannot use proximity, we have to use something else. But there's a very convenient property, actually. Suppose that we have two word embeddings, like v1 and v2 over here, or v1 and v2 over here. We do have this property that if you take those two vectors, and if you do a dot product between them, typically if the dot product is big, that's an indication that they have a similar meaning. And if the two vectors are very dissimilar, then the dot product between them is almost zero. Now we have to be careful with what exactly we mean with similarity here, there's subtleties, but if nothing else, we can take it as a proxy. If two word embeddings are similar, the dot product between them should be big. So then, how about we just use a reweighing mechanism based on just that? What I'll do is I'll take the dot product of my vector that I'm interested in, so let's say I'm interested in the vector of bank in this first sentence, and I can cross multiply that with everything in here. And then, because of and the, they're like stop words, they probably don't have a very high similarity, we can plausibly expect these to maybe have a low overlap. And v1 will have a pretty big overlap with itself, right? It's a perfect overlap, so that should be high. But you can also imagine that bank and river, if these are pre-trained word embeddings, then there should also be some similarity here. More, at least, than in these two. And the interesting thing is you can also imagine that happening in other sentences. Money and bank are plausibly more related than the word the and bank. And that's because the word the and on, again, are really, really general. So that means that I might have a little reweighing scheme going for myself over here. That's quite convenient. One thing I should probably do, though, is, and this is partially due to notation, but one thing that would be nice to do is that if we're going to be reweighing properly, then we should normalize this. It would be nice if this was like a probability distribution, that this sums up to 1. It just makes math a little bit easier down the road. So the approach is, if I want to have a more contextualized vector over here, what I first have to do is do the dot product. After that, what I have to do is make sure I've got a normalized set of weights, and then I can use that set of weights, and this is just the mathematical notation of it, but essentially I'm just using this as a reweighing method to reweigh all of these separate vectors such that this is more contextualized, so to say. Now I hope that intuitively you would agree that what we're doing here is very similar to what we're doing in the time series task. The main difference being that in the time series task, the way that we were making this attention over here, the way that we said, hey, this is how we're going to reweigh, that was based on proximity in time. Points that are far away in a time series task typically should not influence your prediction for now. But in the language task, this might actually be the case. It can be that words that are far away in a sentence are actually giving a lot of meaning. And that is why we are going to have an attention mechanism here that's not based on proximity, but instead is based merely on meaning of words, meaning of tokens. Another popular term for this is self-attention. You're using attention mechanisms based on the information that you currently already possess. So with that mentioned, let's move this into a neural network layer. Because what we can do now is we can move these operations into a layer such that we might be able to import it from something like Keras or TensorFlow. So schematically, we can have a situation that looks like this. We have a bunch of vectors going into this self-attention block, and what comes out is a bag of vectors that just have a little bit more context. And everything that's happening inside of this block, well, that's essentially everything that's happening here. The stuff that's happening here is what goes there. And we then have a nice little Lego brick where something goes in and something goes out. But the interesting thing is, if you take that self-attention block and you were just to maybe add a couple of extra layers before and a couple of extra layers after, but without going into detail, if we just surround that self-attention block with some extra layers, then essentially, that's a transformer. The main component that is inside of a transformer, the main component that adds this behavior that we're interested in, this context from the beginning and the end of the sentence, that mixing, well, the main mechanism that achieves that inside of the transformer is attention. And I am definitely glancing over quite a few details here at the moment, and that's because the goal is intuition in the interest of time. But the transformer, if you formally look at the diagram, has this attention mechanism that's in the core of it. All the other layers around it are somewhat more standard. But the cool thing about this transformer is that it also works on items that are not text. You can also give it other data, and it can still work in a similar fashion. And that's where we come back to our original dialogue. So let's go all the way back to the original problem that we had. We have this conversation, and then we'd like to pick the best next action to take. Well, in that situation, a user might be able to say, hey, I'd like to have a pizza. And at that point in time, we might know a few things. We might have an intent. We have an intent classifier, so we might know what intent that we have. We might have an entity. We also might have some long-term information stored, say things like the user's address or something like that. And we also know the previous action that we took. And you could say that at this point in time, instead of having a word embedding, we just have this feature space at our disposal. We just know these things at this point in time in the dialogue. So given these features at this point in time, we would like to have some sort of a model where this can go in and the next best action can come out. But not just that, we would also like it to work in such a way that if we had not just the current features, but also maybe the previous ones from the previous dialogue step, that we can then use all of that information together to predict the next best action. And as you might be able to imagine, this model over here, that has a transformer. And that transformer, one of the main components in it, is the attention mechanism. And that way, to predict this action, we might be able to say, the context that we need to predict that action, that comes from 2 time steps back instead of just 1 time step back. Just like the bank and river example, we don't want to have a system here where attention goes by merit of proximity. We might have to look back further. And by using a transformer with its attention mechanism, we might be able to have a really nice model at our disposal here. This model, however, is not going to work if we only allow it to look back, say, 2 time steps. It would work a lot better if we said, no, you're allowed to look many time steps back. And exactly that was the problem with the original configuration file that we started with. So what I would like to do now is change that configuration file and see if the chatbot works better. So right now we are back at where we started in the beginning. The only thing that I've now done is I've set the max history to 10, which means that we're looking back way further than we did before. The digital assistant is allowed to look back further for context on which it can base its next action. And what I'm going to do now is I'm going to try to see if I can fool it, but as we will see, it's definitely more robust than it was before. So I can say hello. I can ask it to start counting. So far, so good. And now I can ask, are you a bot? And so far, it seems to pick it up quite nicely and consistently. So what sort of conclusion can we draw from all of this? Well, it might just be a single hyperparameter number over here, but we see that it actually has quite a lot of effect. Now, the example that I have here is slightly artificial in the sense that counting down might not be the most practical use case, but it does serve as a nice example, I would argue, that it really helps to have context from the past still be applicable in the next best action that the digital assistant is supposed to predict. So I think that that's an interesting point to at least observe. And second, what I think is really interesting about this particular example is that the digital assistant seems to generalize quite a bit. I've open sourced this digital assistant, so you can have a play with this yourself as well. And you'll notice that I have a couple of stories here that describe how the conversation might go wrong, but I've not enumerated all the possible options. What actually is happening here is the chatbot is learning that it has to generalize here as well. And that is something that is also happening because of the way that this attention mechanism works. Time to wrap up. I hope that this short demonstration has made the attention mechanism, which I would argue is the main component inside of the transformer architecture, a little more intuitive. In the interest of time, I unfortunately had to skip a lot of details, but if you're interested, I would like you to know that I maintain a playlist on YouTube where I discuss related NLP algorithms in depth. The playlist is called the Algorithm Whiteboard, and if you're interested in details that I've glanced over today, then I can highly recommend you have a look. Before I leave, I figured it would be good though to end on the non-machine learning related note. I certainly think that the transformer and the attention mechanism underneath it, and I also feel that they are helping us a lot in making better digital assistants. But I also think that algorithms alone are not enough. You really need to take care of your data and also consider topics like conversational design. And the reason is, it might be that the stories that you come up with and the stories that you optimize towards are different than the ones that your users generate. And this is a problem that no algorithm will fix for you, and something you should always keep in the back of your mind. The attention mechanism that we have is great, but if you don't have attention yourself for your users, you're going to be missing out on a lot of valuable information that can also make your digital assistant a lot better. That said, I hope you enjoy the rest of the conference, and feel free to ask me anything later. I'll be at the Digital Rasa stand from time to time today, and I'll also hang around the lobbies. Thanks for listening.